Hello and welcome to the lecture video on proper time and time dilation. In this video, I'll be drawing from the material in Brown, Griffiths, and Tong. So to get started, I'll draw a lab frame coordinate system that has three spatial coordinates, x, y, z, and a time t. Here's a particle in this frame that's moving along following some trajectory. And at the moment in time captured here, it has a velocity v. We can write a small section of the path of this particle as a 4-vector, which I'll call dx. Dx will transform between different inertial frames following the Lorentz transformation. Because this 4-vector obeys the Lorentz transformation, we can define a scalar product of it with itself, which will be invariant under any Lorentz transformation. And the proof for why this expression is invariant under Lorentz transformations is an exercise left for the reader. So I'll slightly rewrite the above expression by combining the three spatial terms of the sum into a dx vector. They'll set this equal to ds squared. And this will be the invariant infinitesimal interval. So we're almost at the point where we can define the proper time, but before that, I'll go back to the figure that we started out with, and I'll define a second frame here, which is the rest frame of the particle. So I'll call this frame S prime, and the coordinates will be x prime, y prime, z prime, and t prime. So because S prime is defined as the rest frame of the particle, we know that the particle will always be fixed at the origin of this frame, which means that dx prime computed in this frame will always be 0. So next, let's compute the invariant infinitesimal interval defined here for the particle in this S prime frame. The dx prime is 0 from above, so this term will go to 0, and we'll be left with c squared dt prime squared. And now we can finally set this equal to c squared d tau squared, where d tau is dt prime. Tau is the proper time, or the particle's own time. Going back to the figure above, we might want to consider the change in the proper time along some certain points in the particle's trajectory. So to do that, we're going to rewrite this invariant infinitesimal interval in a slightly different way. where beta is defined as v over c.
We now have an expression for ds squared, both from the lap frame and from the rest frame of the particle. I'll go ahead and set these expressions equal to each other. We're able to do this because ds squared is an invariant. And next I'll solve this equation for dt. We can also write this as being equal to gamma times d tau, where gamma is the Lorentz factor equal to 1 over the square root of 1 minus beta squared. So next, I'll integrate this equation on both sides. And here I'm explicitly showing that the gamma can depend on the proper time, so the velocity of our particle does not need to be constant. But let's consider the special case where the velocity of the particle is indeed a constant. So in this case, it's pretty simple to solve the equation above. So we'll have delta t equals gamma, which will now be a constant, times delta tau. And we have now derived the equation for time dilation. To see this effect better, let's plug in some values. So suppose that the particle has a constant velocity of half the speed of light. This means that the Lorentz factor will be approximately 1.2. And so delta t for this example will be equal to about 1.2 times delta tau. So this means that for every 1 second that passes for the particle in its own rest frame, 1.2 seconds will pass in the lap frame. To conclude the discussion on the proper time, I'll make a quick note that the proper time is used in the definition of the four velocity. This 4 vector is equal to dx over d tau. We can also define a 4 momentum, which will be equal to mass times the 4 velocity. In the last part of this lecture, I'll talk about a different way that we can see time dilation happening in inertial frames. This example is from Griffiths, and I think it's a nice intuitive way to see time dilation. So suppose that we're on a train that's moving at a constant velocity relative to the Earth. If we had a light bulb on the ceiling of this train, the question is how long would it take a ray of light to reach the base of the train? So first, let's solve this problem in the train frame. In this frame, the light ray goes straight down. So if the train has a height of h, then we know that h equals c times delta t prime. In the Earth frame, the train is traveling forward with some velocity, so the train will be some distance ahead by the time the light ray reaches the ground. So I'll draw the new position here, and this will be the path that the light takes in the Earth frame. So I'll redraw the right triangle from above here. And we know the height of this triangle is h, and the length of the base is v times delta t. So using the Pythagorean theorem, the hypotenuse here is h squared plus v squared times delta t squared. So next we can say that h squared plus v squared delta t squared is equal to c times delta t. And delta t here is the time that it takes the light in the Earth frame. So finally, let's solve this equation for delta t. And note that from above, delta t prime is equal to h over c, so I'll make that substitution. And we have recovered the same time dilation formula that we have found above. This concludes proper time and time dilation. Thanks for watching.